I'd like to show you a simple formula, which is why I keep building receivers like this. It's a simple 7 MHz CW only receiver with quite amazing performance. It's a superhet using many of the modules that we've described in a previous video. I could have used a DDS, but there's still pleasure in a receiver that draws just a few milliamps, yet picks up DX signals from half a world away. The receiver has quite a few stages, but all of them can be boiled down to being either a filter, oscillator, amplifier or mixer. I won't present the whole circuit here. Additional information, including building and designing a whole receiver, is found in the book Experimental Methods for RF Design, where similar receivers to this are described. As for the serendipity, that can come from finding two of these crystals that when mixed together can provide a desired sum or difference, suitable for a receiver or transmitter. It's even better if the crystals are standard off-the-shelf frequencies, so you don't have to rely on an extensive junk box to duplicate. A further bonus is if you can use commonly available frequencies to operate on 2 or more bands, especially if those bands are desired and useful for QRP. As DeMoore and Hayward said many years ago, 40 and 20 meters is a great band combination that allows DX and local stations to be worked day and night at most phases of the solar cycle. The IF of this receiver that I'm using is 4.032 MHz, which is a commonly available crystal frequency. For 7 MHz, we need either 3 MHz or 11 MHz to provide the difference at this desired IF. As it so happens, you can buy crystals for 11.059 MHz. The difference between the two is 7.027 MHz, or inside the CW portion of 40 meters. If that's your IF and that's your local oscillator, you can add some inductance in series with this crystal to pull its frequency down. Even better is if you have two crystals in parallel with a super VXO arrangement. Then you'll be able to obtain some frequency agility. For instance, if we were to make this 11.039, then we get down to 7.007. That 20 kHz span in the bottom end of the 40 meter band is popular for DX stations, particularly from Europe. Now another thing with VXOs is if you use a very small series capacitance, then you can increase the frequency to a bit above the marked one on the crystal. That will give you a higher frequency up above 7030. Another common off-the-shelf frequency is 10 MHz. Do the sum, not a subtraction this time, and we get 14.032 MHz, putting it in the 20 meter CW end of the band. Therefore, with a 4.032 MHz IF, you could make a dual band receiver or transceiver. Again, with a good VXO, you should be able to get a 20 kHz range, getting you coverage down to 14.012. It won't cover all of the CW segment, but it should cover a reasonable chunk. If you do want to make a dual band receiver following this principle, I suggest using a dual gang variable capacitor. The benefit of having a dual gang variable capacitor is you can have the sections used for two separate oscillators. One with an 11.059 MHz crystal for operation on 40 meters, and another with a 10 MHz crystal for operation on 20 meters. Having the separate oscillators makes it possible to optimize the inductance and capacitance values for each one and obtain the most stable VXO pulling range. The switching between the oscillators is simple. You just apply power to whichever one you want to operate on, and you feed them to a common buffer, and that goes to the rest of the receiver or transceiver. The only other parts of the circuit in a receiver where you'd be band switching would be the front end, and you can just use a relay or double pole double throw switch for that. Or if you want it to be crude, this is your receive front end tuned circuit, optimized for 14 MHz. That might be your antenna connection. might be a coupling capacitor here to the front end. Then if you had this on 14 megahertz, you could just switch in another capacitor to provide some added capacitance for 7 megahertz. You've just heard an example of the joys of serendipity, using cheap and commonly available crystals to provide useful coverage of two amateur bands. Now we'll go through the block diagram and describe the stages in a bit more detail. A quick tour through the block diagram. Incoming signals at 7 MHz, negotiate a bandpass filter. I'm using two 4.7 microhenry RF chokes. A good rule of thumb with those is they need about 100 picofarads in parallel to resonate on 7 MHz. So there's some low value trimmer capacitors and some other parallel capacitors there to make up the difference. If you're really sloppy, you can just put in a 100 picofarad fixed capacitor, but it might not quite be on the nose for 7 MHz. The twisted wire you see here provides 1 or 2 picofarads of capacitance between the two sections of the bandpass filter. That's good if you don't have 1 or 2 picofarads in the junk box. It's sometimes called a gimmick capacitor, just 20 or 30 millimeters of twisted wire. There's an RF amplifier, very simple, just using a BC548, though you could use a 2N3904 or even a 2N2222 instead. The RF preamp provides an incoming signal to the first mixer, the part of the receiver that converts the 7 MHz incoming signal to our 4 MHz IF. There are 4 diodes, 1 in 914s, and 2 ferrites. You can use either toroids, or as I've used here, 2-hole TV Ballon formers. The signal into the mixer is beated against your local oscillator signal, which is our VXO. That comprises of our 11.059 MHz crystals, 2 of them in parallel to provide a decent tuning range. There is a buffer immediately following that to improve stability and provide a bit of amplification. Just to the right of the centre, you can see the 2 crystals in parallel. There's some RF chokes as well, and they lead to the variable capacitor, an airspace type with a maximum value of 50 or 100 picofarads. If you don't have an air-spaced variable capacitor, you can use a plastic type. Stability might not be so good, but it should be acceptable in this application. Or if you don't have that, you could use varactor diodes. You won't get quite as big tuning range as with a air-spaced variable capacitor, but it should still be usable. The function of all this is to convert the incoming 7 MHz signal down to 4 MHz by beating it against the 11 MHz. This signal is very low level, so it needs some amplification. A 1 transistor IF amplifier, then a crystal filter. That's a ladder type of filter. I'll talk about that later on, but it's basically 2 crystals in series with some capacitors that allow a narrow pass band, in this case around 500 Hz. That's followed by another IF amplifier. It's needed because the crystal filter will be attenuating the signal, so it's still very weak. This is one of our IF amplifiers, a BC548 and a few extra components, very similar to that used in the BitX design. The remainder of the IF strip on the right is the 2 crystal filter. The remainder of the IF strip on the right is the crystal filter. It has just 2 crystals and a handful of capacitors. Those values are fairly critical if you want the best bandpass characteristics. I didn't bother with the formulas and just put in values that provided a reasonable selectivity, in this case around 500 Hz. On the left is the second IF amplifier. That feeds the signal to the product detector. Again, that mixer or product detector is exactly the same parts as our first mixer. The product detector gets its driving force from a BFO using a 4.032 MHz crystal and 1 transistor for the oscillator and another for the buffer amplifier, exactly the same as for the 11 MHz local oscillator. You'll see there's a disc ceramic capacitor with quite long leads connecting from the crystal to the base of the oscillator transistor. Changing the value of that capacitor, which is only a few picofarads, allows you to change the value of the beat frequency oscillator's output frequency. Ideally, that needs to be 500 Hz to 1 kHz from the center of the bandpass of the crystal filter. If it's not, your receiver will sound either very tinny or very bassy, and you won't be able to hear CW signals at a comfortable tone. The signal from the IF is beat against a BFO at 4 MHz. It's actually the same frequency as the crystal filter, offset by 1 kHz to provide an audio difference. Our last stage is the audio amplifier. That comprises an LM386 circuit, but there's a few more parts because I'm using the Unleashed LM386 design, which gives a bit more gain. If you have a look at the diagram, a lot of stages are duplicated. There might be 2 or 3 required for a receiver using exactly the same parts, like these mixers, 4 diodes, a couple of broadband ferrite transformers, and that's your mixer. The local oscillators as well, a Colpitts oscillator feeding another transistor as the buffer, exactly the same in both the BFO and the local oscillator, only some slight differences in the crystals and capacitor values. The IF amplifiers, again, they're the same. This is the receiver connected to an antenna, but with no incoming signal. You can quite clearly see the characteristic of the audio. There's a concentration between about 400 and 800 Hz, and the audio either side of that is much attenuated. If I paid more attention to component values, I might have a better shape, but I think this is quite satisfactory. It's possibly unfair because it doesn't have a narrow CW IF filter, but I actually prefer the sound of CW signals on the homebrew receiver compared with the IC751. The S meter is reading S9, so that's the amount of local noise that I have. This has been our look at a simple 7 MHz receiver. It's not for everyone. It only covers a small slice and one mode, i.e. CW. But it shows that if you're willing to specialise and build equipment that does one thing very well, then you can achieve good performance with only a handful of parts. Just a reminder that if you're looking for a comprehensive manual on all aspects of operating QRP, don't go past minimum QRP. A Kindle ebook available for US $4.99. More than 700 have been sold and it's been favourably reviewed. For more information, follow the links from VK3YE.com or search minimum QRP in Amazon.